All right, so welcome back to the lecture, and now we are going to actually use different thresholds and see the effect on the classification report and the confusion matrix. So in order to do this, you just get the predicted probabilities. We are then going to grab the second column, which as we saw in the last lecture, it's the second column that is the probabilities of passing. I'm going to create a copy of that. It's good practice to create a copy if you plan on manipulating the copy. So create a copy and we just call that ypred. And now anywhere ypred is greater than or equal to 0.5, we're starting with the 0.5 threshold. So we're starting with the same threshold that we've always have been using. So wherever that's greater than 0.5, we set it equal to a 1. And where after setting those to a 1, any place it's not a 1, we set to a 0. So this actually gives us, because we're using the same threshold, this gives us the same predicted classes we have always been using. So if you compare this to this, they're the same. Now they print a little differently because these are printing as floats. And we could actually change that just so it looks the same. Whoops. There we go. So we print these as integers, and you can tell these are the exact same. You could also just look at the classification report and the confusion matrix, and you will see they'll be the exact same to the ones up here. Oops, sorry, right here. But now let's change it. Let's move up to 0.8. So what we see is that we actually forecast many less passes, so only 27, whereas before we forecasted 61. And then we forecasted many more fails. Right? So if our threshold is really high at 0.8 for passes, then therefore it's the threshold for a fail is only 0.20, is only 20%. Anything that our model says is any student that the model predicts has a probability of failing 20% or greater, we label as a fail. So we predicted many more failures. We had 52 failures, whereas before we only predicted 18. Our precision is quite a bit less, so only 19 of these 52 are correct. And it's our precision is right here, 37%. Up here, 12 of 18 are correct, so our precision is much higher, 67%. However, up here, of the 25 students that truly fail, we only correctly identified 12 of those. So our recall is about 50%, 48%, right? 12 to 25. Down here, we get 19 of the 25, so our recall is much higher, 76%. Question is, which is better, right? Is it better to have high precision and low recall, or low precision and high recall? And of course, in a perfect world, they'd both be high, right? You'd have a perfect model. Well, it depends on your application. So let me give you a real-world example of when you actually would be okay with a lower precision if you have a high recall. This is something I actually work on. So let's pretend you're shipping food across the country. And if the weather is too hot, so if the truck driving across the country, right, if it gets too hot, the shipment will spoil. And that costs $50,000. I'm making these numbers up. The numbers are different, but let's just pretend it costs $50,000. Now, to protect the truck, to refrigerate the truck, it costs $500. So you'd like to know what trucks to protect, right? You don't have to protect all of them because you're shipping thousands every day, and you don't have to protect all of them. But you want to know which trucks on certain routes are likely to get too hot, so we can protect those. Well, if you think about the math of the costs, right, if you can save one load from spoiling, you have saved $50,000. And to protect only costs $500. So if you do the math, you could protect 100 trucks, and only one of them would have to be one that would have spoiled. And you'd break even, right? So you spend $50,000 on protection and you saved one, which saved you $50,000, so you've broken even. So in that scenario, your precision can be 1% to break even. And you want your recall to be high because you want to identify all of those trucks that will spoil because they're so expensive, right? If you have a low recall, if 10 trucks spoil and you only identified one of them and protected it, well, you still have nine that spoiled. And that's $450,000 in loss. So cost and the benefit of identifying a class are so imbalanced, then you actually want to have a imbalanced threshold, right? You don't want to use a threshold of 0.5. You want to use a threshold that's lower or higher, depending on the application. In the next lecture, we'll see how we can visualize this trade-off by the trade-off of using different thresholds. We'll see it in what's called a ROC curve. All right, back to the lecture. We are going to talk about ROC curves. ROC is short for receiver operating characteristic, and you can learn more about it by clicking here if you'd like to. So to plot an ROC curve, you can use the ROC function from scikit-learn, and then you pass the true values as the first argument, and then the predicted probability as the second argument. And we want to pass the predicted probabilities of passing, which is that second column. So we're passing that. And we run this, and what this gives us is the false positive rate and the recall for all of these thresholds. So recall, we already know what that is. The recall is the percentage of the true labels in the data that you correctly identify. False positive rate is the percentage of the untrue labels in the class that you say are true, or in our words, this is the percentage of the students that actually fail that you identify as passing. So let's go through these examples and we'll just talk through it. So the first threshold is 1.95. Now you're thinking that's ridiculous. The threshold needs to be between 0 and 1. And you're right, but the first threshold when scikit-learn does this is it makes a threshold that's so high that you would call nothing a pass. So it's 1.95, and basically that means, right, your predicted probability of a pass will never be over 1.95. So you forecast nothing as a pass. So your recall is 0% because you're forecasting nothing as a pass, but your false positive rate is also the 0% because you're not calling anything a pass. Now, if you move that threshold to 0.95, now your recall is about 7%. So 7% of the students that actually pass you are correctly identifying as a pass. However, 16% of the students that actually fail, you're also saying they pass. So these are errors. And if you go all the way down to this threshold of 0.38, the reason this is the last threshold you'll see in a minute, but now with this threshold, we're calling everything with a predicted pass probability of greater than 38% a pass. So our recall is 100%. So at this threshold, every student that passes, we correctly identify as a pass. However, every student that fails, see the one here, the one for the false positive rate, every student that fails, we also said would pass. We basically just said everybody's going to pass. And, that's not always good, right? And that's why the threshold stopped here. Once you get to a recall and FPR of 1, then you don't need to go any lower on your thresholds. So the recall and the FPR always range from 0 to 1. All right. So let's visualize this. Oops, the error. Now let's visualize it. So we can actually visualize the trade-off from the recall and the false positive rate. And sorry, I had a typo in a label. I'm just going to fix it. Okay, here we go. We can, the recall versus the false positive rate. So what we are seeing is the trade-off for different thresholds. Now the threshold itself, you can't tell from the plot, but we can do a little work here to find it out. So notice that when the recall, sorry, I'm going to call this recall, even though another name is true positive rate. So when the recall is 0, and the false positive rate is 0, we have a dot here. That's when the threshold is 1.95. Now let's look at this point. The recall is almost 40%, and the false positive rate is about 0.25. So we actually see that right here. The recall is about 40%. This is the third value, and the false positive rate is about 0.25, 25%. So this is the third threshold. So this corresponds to a threshold, a decision threshold of 88%. And as we move that threshold up, we see this trade-off change, right? As we lower the threshold, where actually the threshold is descending. So as we lower the threshold, our recall for passes increases, but so does our false positive rate. So you can see like your different trade-offs and what you might want. If you want to have a large recall and you don't mind having a large false positive rate, like in the shipping food example, you might want to dot up here, right? Now let's talk about a perfect model. What would a perfect model's ROC curve look like? Well, it would actually be a straight line all the way up to 1, and then it would go all the way over. So that's how you want your curve to be. You actually want what's called the maximum area under the curve. So you want your curve to go straight up and straight over. And let's think why. Well, in an ideal world, your probability that the model outputs will be a 0 if the true class is in our case, let's say it's our case of dealing with passes and fails. If the true class is a fail, you want the predicted probability to be 0. You want your model to be very confident, right? And if it's if it's a pass, you want the predicted probability to be 1. So you want a situation where you're recalling every single pass, and you're not identifying any of the of the fails as passes. So you're correctly identifying all the passes, but you're not incorrectly identifying any of the fails. So that would be a value all the way up at 1. Boom. And then, of course, eventually, if you turn the threshold down enough, you will then call everything a pass. So your recall will be 1, and your false alarm rate, your false positive rate will be 1. But you want to have that point where the recall is 1 and the false positive rate is 0. So that's what a perfect model, which doesn't ever happen except, on fake made up data. All right, I'm going to do one more example with this in the next lecture.